For a software system to survive, it can't stand still. It has to constantly adapt, grow, and reshape itself to handle new demands. Think of an API as a rigid digital contract between different components, a binding promise that defines exactly what inputs are accepted and what outputs are guaranteed. When you alter that API, you are modifying a signed agreement. If you change the rules without warning, you violate that contract, and the penalty for breaking that trust is immediate failure. Imagine a developer wants to improve the way an application fetches tasks from a database, so they decide to clean up the data it sends back. This chart shows the original API output, a standard JSON response doc delivering two required pieces of data, an ID and a title. The developer decides name is a more accurate description. They go in and simply swap out the field. But a front-end application is still expecting a title. When it gets nothing back, the system turns red and shuts down. Old applications are hard-coded to the original contract. They cannot dynamically guess that you renamed a field. Because of one minor tweak, external system integrations fail, mobile applications suddenly crash, and debugging becomes pure chaos. Overriding an active API forces a lethal disconnect, severing access for every user still running the old integration. To avoid this, major platforms like Stripe or X don't delete old code when they upgrade. Instead, they use versioning to host multiple parallel realities simultaneously. This diagram illustrates branching. The central server receives incoming traffic and splits it into distinct, isolated paths, labeled V1 and V2. Legacy systems flow safely down V1, untouched. Meanwhile, updated applications travel down V2. Both operate smoothly at the same time. Versioning allows a system to introduce an upgraded reality without destroying the world that existing users currently live in. But this raises an engineering question. How do developers know when a new version is required versus when they can safely update the current code? The answer lies in identifying whether an update is a safe mutation. A safe mutation is an addition that doesn't violate the existing contract, like adding purely optional fields. In this visualization, watch the JSON data block. A new line of data is added at the bottom, but the existing fields above it remain completely undisturbed. Because the original promise is kept intact, old clients simply ignore the extra data. Safe mutations do not require a new API version. A breaking change is different. It happens when you rename keys, alter behavior, or change data types. Here, the JSON block switches a field from text to a number. Unprepared for this format, the receiving app's parser connection shatters immediately. If an update modifies the original promise made to the front end in any way, a new version must be born to prevent a total collapse. This concept becomes critically important when building with modern AI coding assistants. These tools iterate on code at blinding speeds. While trying to find the most efficient solution, an AI will frequently rewrite endpoints and rename API fields silently in the background, just to optimize a local chunk of code. Without strict versioning rules acting as guardrails, that speed of iteration simply becomes a mechanism for rapid system collapse. This is why you have to enforce a very specific directive when prompting AI. Do not break existing API contracts, version instead. Maintaining these parallel structures is a non-negotiable survival requirement for scalable architecture. Without this safety net, growth inevitably leads to breakage. The only safe way to build the future of a system is by hosting it simultaneously with its past. Next, we'll look at how to protect that system from being crushed under the weight of its own data by mastering pagination.